Welcome back to Discrete Mathematics. Today we're going to look at some coefficient extraction and something called the extended binomial theorem. So, last video we did some examples and we didn't find any specific answers, but we looked at how we can solve problems using generating functions and what some of those generating functions are. So here we'll talk about coefficient extraction, which is pretty much getting the answer we want. So what we do is we put this in little square brackets and we say this is the coefficient of x to the n. So if we take a look at the coefficient of a regular power series, then if we want the coefficient of x to the n, then our output is going to be a to the n, or a sub n, because that is the coefficient of x to the n. So pretty simple definition, not too bad. So here's a basic question. What is the seventh, or x to the 7? What is the coefficient of x to the 7 in the expansion of 2x plus 4 all raised to the 10? Well, this is just the binomial theorem. Of course, you'll remember this from the first discrete math course. And if you don't remember, x plus y to the n is the sum of I equals 0 to n of n choose I times x to the I y to the n minus I. So a little bit complicated, but we'll see it in action here. So we want x to the 7. So what this really means is that we want 10 choose 7. We want 2 times x to the 7, which means that this y value, 4, is going to be to the 10 minus 7, which is the same thing as 4 to the 3. So I'm not going to simplify it really anymore, but essentially what we've done here is we've taken our x, and this is our y, and because we're looking at the 7th power, of course we want our x to have the 7th power, and we should be choosing the 7th power as well, which is denoted up here in this sum as n choose I x to the I. So that is the coefficient of x to the 7. So you've kind of done this before, but just not maybe with this notation. Of course, we can make things a little bit more challenging, but before we do that, I need to teach you this extended binomial theorem, otherwise you won't be able to find out some of the more difficult coefficients. So we've used the definition n choose r before to be n factorial over r factorial times n minus r factorial, and that works, but the problem is that it assumes this is a real, an integer, positive integer, but we can use the binomial theorem for more abstract things, like what does a third choose 2? Well, we need to use this definition up here, which is n times n minus 1 times n minus 2 all the way down to n minus r plus 1 all over r factorial. You can see this follows from this definition here. So what we're doing is I want to get rid of this n minus r factorial at the bottom. So what I do is I just expand n all the way out until I get to n minus r plus 1 and then n minus r factorial, and then I just cancel it here. So this follows from the old definition, and what's cool is that we can put in any number we want now. So let's do 1/3 choose 2. So we have 1/3 times, well, we want 1/3 minus 1 now, and we only wanted 2 terms, so that's good for the top. And we're choosing 2, so it's over 2 factorial. So this is just going to be 1/3 times negative 2/3 over 2 factorial, which is the same as negative 2 over 9 all over 2 factorial. So this is going to be negative 1 over 9. So 1/3 choose 2 is negative 1/9. And you're saying, hold on a second, you can't choose 2 of a third of an object. You are right. You're absolutely right. But it's a little bit more abstract. You know, you can't choose 2 out of a third. So this is one of those things that follows mathematically and works absolutely properly, but might not make intuitive sense. So understand the abstraction behind it, and you'll see its use in just a few moments. But first, we can do it for negative numbers too. So here's where it even gets stranger. What does negative 6 choose 2? Hold on a second. Do you want to choose 2 objects out of negative 6? Are you crazy? What do you mean choose 2 objects out of negative 6? You can't do that. Well, with our definition of the expansion of the n choose r operator, we can. So I've written out a few steps here. I'll go through this. So in the first step, we start out with negative n. We go all the way down to negative n minus r plus 1 all over r factorial. This is the same as the previous example. Then what we do is we factor out a negative 1 from each of these terms. So we get a negative 1 to the r here. Just like we did, well, not just like we did, but because there's r terms, because we're choosing r terms, we can factor out negative 1 r times. So we get negative 1 to the r. And then what we do is we just kind of reverse the step we did in the last page, and we change this to n plus r minus 1 factorial. Notice it only goes down to n. So it's n plus r minus 1 all the way down to n. So we have to sort of add in this n minus 1 factorial on the top and the bottom to cancel out, and we end up with this result at the bottom here. So negative n choose r is just negative 1 to the r times n plus r minus 1 factorial over r factorial times n minus 1 factorial, which simplifies to n plus r minus 1 choose r times negative 1 to the r. Because this is just the definition of n plus r minus 1 choose r. So what's interesting is that when we have a negative n, we end up with the combinations with repetition formula, with, of course, this negative 1 to the r, which depends whether it's positive or, sorry, even or odd. But it's kind of an interesting result. So let's do a couple examples. Well, I'm going to leave this formula over here on the side. Negative n choose r is equal to n plus r minus 1 choose r times negative 1 to the r, because I think it's more important to be able to do these quickly than it is to write out every single step. So we know that this is just going to equal 6 plus 10 minus 1 choose 10 times negative 1 to the 10. So this is just going to be 15 choose 10. So negative 6 choose 10 is just the same thing as saying 15 choose 10. What about negative 17 choose 9? Well, this is going to be 17 plus 10 minus 1 choose 9. Sorry, that should be plus 9 minus 1. Then we get negative 1 to the 9. So we're going to get negative 17 plus 9 is 26, minus 1 is 25, choose 9. And of course, this negative comes from the fact that we have an odd r value. So pretty simple, actually, to do negative expansions. It's kind of interesting, I think. And the question is, why do we need to know this? Why do we need to have the extended binomial theorem to include negatives? Well, here's why. I want the coefficient of 1 over 1 minus x to the 4. Now, how do we do that? Because we're dealing with negative x's here. So, first of all, we can rewrite this. We can make this a little bit nicer. So this is x to the 6 of 1 minus x to the negative 4. Okay. So when we have this example, this value right here is our n, and this value right here is our r. Now, why is it this way? Well, we have negative 4, and we're choosing 6 of them. So this x6 is actually equal to negative 4 choose 6. And of course, because we're dealing with this negative x here as well, because we're using the binomial theorem, we have to include this negative x to the 6 as well, because we're choosing negative x, or 6 negative x's. So what happens here is, with the expansion before, we get 4 plus 6 minus 1 choose 6 times negative 1 to the 6 because of our expansion. And we'll split up this negative x here, and we'll split it into negative 1 to the 6th times x to the 6th. Well, because we're looking at only the coefficient, we really don't need this x to the 6 here. That's not really important. And you'll also see that we have a negative 1 and a negative 1 canceling each other, because a negative times a negative is a positive. So our end result really is just 9 choose 6. So the coefficient of x to the 6th in 1 over 1 minus x to the 4 is just 9 choose 6. So if you ever have a 1 minus x on the bottom, your answer is always going to be positive because your negative 1s will cancel out. It's kind of cool. So that was a fairly straightforward one, I would say. And let's make it a little bit harder. Okay, what is the coefficient of x to the 8 of x to the 4th over 1 minus 3x squared? Okay, well, how do we deal it with when we have this x to the 4 on top? Well, here's the thing. We've kind of just shifted this 1 over 1 minus 3x squared function. We sort of just shifted it over by x to the 4. So we can rewrite this as actually just saying, what is the 4th coefficient of 1 over 1 minus 3x squared? You're saying, hold on a second, why does this work? Well, think of it as saying, well, every term is going to be shifted over by x to the 4. So we're multiplying the whole function by x to the 4. So why don't we just put that x to the 4 back into x to the 8 and see what we have left? So that's what we did. Now we want the 4th coefficient of 1 over 1 minus 3x squared. Well, again, we can rewrite this a little bit nicer. So this is going to be 1 minus 3x to the negative 2. And again, we have an n value here. We have an r value here. So let's plug those in. This is negative 2 choose 4 of negative 3x to the 4. And we can expand this. So this will be 2 plus 4 minus 1 choose 4 times negative 1 to the 4. And that is the expansion of negative 2 choose 4. Now we'll expand negative 3x to the 4. This is just going to be negative 3 to the 4. And we don't need the x to the 4 because we're only looking at the coefficient. So we get our result as 5 choose 4. This negative 1 and negative 3, they'll end up becoming positive. So this is really just 5 choose 4 times 3 to the 4, which we know was just 5 times 81. So we can actually compute that, which we know is a 405. So what this says is that if we take x to the 4 of 1 minus 3x squared, we'll get 405. So when we shift everything over by 4 values, it'll be the 8th coefficient of x to the 4 over 1 minus 3x squared. So that's a little bit more of a tricky example. Of course, you can plug these equations into Wolfram Alpha, and you can check for yourself that these are indeed the coefficients. So that's a nice way you can check. You can just plug the function right in, and you can search for that x value. So that's a great way to check your answers. Let's do a word problem. These are fun. If a fair die is rolled 12 times, how many ways can they sum up to 30? Okay, so we need to think about this a bit. We want them to sum up to 30. So we're going to want the 30th coefficient of some equation. And what's the equation? Well, a fair die, this is going to have 6 sides in this question, so it's a 6-sided die. So what are the options? The options are going to be 1, 2, 3, 4, 5, and 6. And we roll this 12 times, so we'll pick one of these each time for 12 rolls. So, what do we do here? Okay, well, x30 of x plus x squared plus x cubed. We need to factor out an x out of all of these, because we want our generating function to start at 1. So we'll just take an x out. So this will be x30 of, well, we're going to take an x out of the first one, we're going to take an x out of the second one, out of the third one, out of the fourth one, and so on. So we're going to take 12 x's out over the course of this. This will be x to the 30th coefficient of x12 times 1 plus x squared plus x cubed plus x fourth plus x to the 5th, all to the 12th. We'll do what we did in the last equation, and we'll just shift it over. So really what we're looking at here is x to the 18 of 1 plus x squared all the way up to x to the 5 raised to the 12th power. Now things get a little bit trickier, because what is this generating function? Well, this is, of course, the 18th coefficient of 1 minus x to the 6th over 1 minus x. This was talked about in the previous video, so if you can't see this, please refer back to that one. And this is raised to the 12th power. Okay, so let's write this a little bit nicer. This is x to the 18 of 1 minus x to the 6th all to the 12th times 1 minus x to the negative 12th. This is where things get tricky. In fact, it's where it gets very tricky. So listen up very closely to this. I had troubles with this for quite a while. Never really understood it till I got to my final exam in the course, and it wasn't even used there, so how disappointing, right? But we need it to sum to 18. So these are two different binomial expansions. One is a negative 12, one is a 12. We need to choose 18 total. So what we want is all possible combinations. So let's suppose we have different cases here, because we need different cases to do this. In the first case, in the first section, we have 12 as our n. We're going to choose 0 of the x to the 6's, which means that we have to choose 18 out of the second part here. So this will be on blue. So we're going to choose 18 out of negative 12, because we don't have any x6's, and we have to get up to x18. So we have to choose 18 of the x1's. Now, what about the case where we choose 1 of the x6's? So let's 12 choose 1. And if we have x6, then that means we have to choose 12 out of the x1's. So this will be negative 12, choose 12. And what also should be noted here is that because I'm only choosing one of the x6's, when I expand it, I'm going to get a negative 1 times x to the 6 here. Because this is a negative number, negative x to the 6th, and I'm choosing 1. So my answer is going to be multiplied by negative 1. So put that negative 1 there. Let's add the next part. Suppose I choose 2 x6's. So 12 choose 2 of those. Okay. So I have x to the 12 now. So I have to choose 6 more of the x1's. So it'll be negative 12, choose 6. And then our last case, well, suppose I choose all three x6s. Of course, it's going to be -1 because we're choosing three negative numbers. And that means that we can't choose any of the x1s. So it'll be -12, choose 0. So these are all the cases we have. And it's amazing, right? Because there's, you're multiplying two numbers, so you think, okay, we just multiply a bunch of things. But you have to consider all the cases where, okay, we choose 1 out of the first one, we choose 2 out of the first one, 3 out of the first one. I could choose 4 out of the first one now, but then we'd be at x to the 24, and we can't have that. So now we can do some simplifying. Well, 12 choose 0 is just 1, so we have -12 choose 18. We're going to subtract 12 choose 1 times -12 choose 12. We'll add 12 choose 2 times -12 choose 6, and then we'll subtract 12 choose 3, and -12 choose 0 is just 1. So we can simplify this further. This will be 29 choose 18, because 12 plus 18 minus 1 is 29. We'll subtract 12 times 23 choose 12. We will add 12 choose 2 times 17 choose 6, and we'll just subtract 12 choose 3. So that would be the answer. It's kind of difficult. I know it's difficult. And originally this was a probability question, but I decided against doing the probability version because really it's taking away from the, okay, how do I do this difficult generating function? And it's putting it more into a, oh, what's the extra step here? And that's not necessary for a video on how to learn to do this stuff. So that was the probability example. Let's do one quick one here. In fact, this is your practice, so please do it right now if you can. Okay, well, you can pause the video if you want to try it. So we'll do the same thing here. We're going to take an x6 out of all 6 of these. So we're going to take x36 out. And we'll be left with 1 plus x squared plus ... And of course, we want the 50th coefficient. Because this is shifted over now, we'll just shift it back, and we'll be left with x to the 14 of 1 plus x squared plus ... And this is, pretty simple now, because this is just saying I want x14 of 1 over 1 minus x. And we know that 1 over 1 minus x just is the 14th coefficient of 1 plus x squared plus x cubed plus ... forever. So this is really just 1. And it's a fun question because you do have to do some steps here. So to get to the part where the answer is simple, you have to know the method to get there. So it's kind of a fun question. Anyways, that was extracting coefficients. There's still another video on another scenario for extracting coefficients that we're going to do next time. So as always, if you have any questions, leave them in the comments below. And if you want to see more of this stuff, of course, you can check out the playlist on YouTube or go to trevtutor.com and check out the Discrete Math 2 section. So I'll see you guys next time.